In 2012, Apache Hadoop 1.0 is released, and I forgot the year, and I didn't include that. I think in 2013 is where Apache Hadoop version 2.0 is released. And 2.0 is, I think we are currently, for this tutorial, we are using Hadoop version 2.7.2. And Hadoop 3.0 is on the way, I think, scheduled for the next year. So Hadoop in itself Hadoop in itself is not very. After you go through this, you will see that the concept of Hadoop is extremely simple. What really important about Hadoop is that it's basically create an infrastructure that everything else is reusing in order to deal with big data. So going back to the two papers that we will release, the GMS paper and the MapReduce paper, a lot of people the MapReduce paper actually have a higher citation count than the GMS paper. But I consider the GMS paper as the most important element within the entire Hadoop infrastructure because it describes how you distribute and place data across the entire cluster of machines. The MapReduce paper describes how you do it, and there are many different ways that you can re-implement how you deal with data distributed that way. But to store data, there's only this one way, and basically you can have different flavor of MapReduce going forward, but there will be a single version of HDFS that is being reused. So what makes HDFS different from all of the other traditional way? So there are three approaches in storing data for processing. So the traditional one we have done it since the ancient time. You have a single computer, you store your data on the computer, and you try to work from your computer. The second way is what we see with systems like the Palmetto supercomputer. We see we have a compute node. Storage is responsible for doing the calculation, but then we also have a massive parallel file system on the back end that all of this compute node have access to and get the data from. The data is going to be moved. So for the second model, the data is going to be moved from this massive parallel file system over to the compute node for calculation purposes, and the data is basically being moved across the network. What happens then is, as you start to have more and more data, and particularly in the shared research computing systems such as Palmetto, where you have many researchers working on the same computing hardware, this becomes a bottleneck. So not only do you have to read the data from the hard drive, you have to move it across the network, which the speed is much slower than trying to read the data internally. And then you have many people trying to read the data at once. So not only the speed, but the bandwidth of the network become a bottleneck. The single computer approach model is very fast. You can move as much data as you want. There is no contention with other users. But you are limited to how much data you can store within a single computer. So the approach of HDFS is quite simple. So basically, they are still using a network computer, but they are assuming that the CPU is co-located with the data storage. So basically, for example, take this example, the CPU in this case is only responsible for data transfer and read and write, but now it is also going to be responsible for the calculation. So most of the data, instead of having to move across the network, is going to be analyzed on-site on this hard drive. And so you don't have to move the data across the network. So this concept is called data locality. In other words, you don't want to move In this case, you are moving the data to the computation. In this case, you are moving the computation to the data. So that's the difference between a traditional high-performance computing approach and a scale-out Hadoop-based data-intensive computing approach. And again, I want to say that one is not better than the other. This is apple and oranges. You pick the one that is most appropriate for your project. So these are the 6 assumptions that Google listed within the paper. The first assumption is hardware failure is the norm rather than the exception. They run data warehouse that have tens of thousands of machines, and Google released a trace storage data of one of their warehouse for 1 month. The warehouse has 12,000 machines, and I think there was about close to 1,000 instances of machine failure within that month alone. So instead of trying to prevent failure, it's more realistic to recognize failure and understand how to deal with it. The second assumption is that data arrive as a stream. So data arrive as a stream, that means you want to process massive amount of data in batches. It also means that this is somewhat related to this point. Data arriving as a stream, and you want to be able to read all the data through the data. You want to be able to provide it once, but you read the data many times. There is no modification on a data stream. And so on HDFS, you will see that once you place a data set into HDFS, it stays there. If you want to make changes to that data set, you better take it out, do the modification, and put it back in. You cannot do the modification of data inside HDFS. The amount of data processed is going to be very large. I used to give this lecture and I used to talk about terabytes of data, but nowadays, large data, that means you need to have hundreds of terabytes of data or petabytes of data. And of course, the assumption that it is cheaper to move the computation, so this means copy the programs to the computing node rather than trying to move the data to the computing node. And also, because of this, because of the fact that you have to replace machine very frequently, it's also led to the case that when you replace a machine or when you want to upgrade the machine, it is not going to be guaranteed that you can have the same model of computer again. Computer is developing very fast now. So this infrastructure can support a cluster consisting of computers of different types of hardware and software. HDFS should be impervious to what kind of hardware and software that you are running in.